An integral component of a typical motor control system is a motor controller. A motor controller is a device or a group of devices whose purpose is to control and protect a motor. Physically, a motor controller may be located quite a distance away from the motor that it controls. Electrically, the motor controller is located between the facility's power supply and the motor. Motor controllers for the motors in an area of a facility are often grouped together inside a common housing called a motor control center, or MCC for short. In many cases, an MCC houses the controllers for the motors in a particular process. An MCC may also contain other electrical devices, such as circuit breakers and switches. One device that is often part of a motor controller is an electromagnetic switch known as a contactor or motor starter. When the contactor is operated, it allows current to pass through the controller to the motor. This is a simplified illustration of one type of contactor. During operation, current is supplied to a coil inside the contactor. This coil is known as the operating coil or the M coil. An iron core inside the M coil concentrates the magnetic field. When the M coil is energized, it becomes an electromagnet and attracts an armature. This moves a set of movable contacts against a set of stationary contacts. The armature is connected to a pair of springs, which are compressed as the armature is pulled down. When the contacts close, a complete path for current flow is established through the controller to the motor. When the M coil is de-energized, the electromagnetic field is removed, and the springs push the armature back to its original position, separating the two contacts. One advantage of using a contactor in an AC motor controller is that it can be energized from a remote location using a voltage that is lower than the motor's operating voltage. The power circuit is energized or de-energized by devices operated by the lower voltage control circuit. This protects personnel from high voltage hazards when they start and stop high voltage motors. An AC motor controller typically has 3 sets of contacts, one set for each of the 3 phases of power in the AC power circuit. A motor controller may also have additional sets of contacts called auxiliary contacts. Auxiliary contacts are usually attached to the armature and operated by it. These contacts are used to perform auxiliary control functions, such as providing current for indicating lights, like the ones used to indicate whether a motor is on or off. Now, in addition to controlling the operation of a motor, motor controllers usually protect the motor as well. For example, motors are rated to deliver a certain amount of power. If demand on the motor increases, current flow through the motor increases. If the current is allowed to exceed the rated capacity of the motor's stator windings could be damaged. In addition, the rotor and possibly other parts could be damaged by excessive current. Motor controllers typically contain overload devices. When these devices detect excessive levels of current that are associated with overload conditions, they shut down the motor before damage occurs. When an overload causes a motor to shut down, the cause of the overload must be determined. After the problem is corrected, the motor can be restarted. Many motor controllers have a reset button that must be operated to reset the controller after an overload. As a general rule, a motor controller should be reset only once after an overload. If it's reset more than once and the motor is started over and over, the motor's windings could be damaged. This is a simplified electrical diagram of an AC motor controller. Electrical diagrams use letters, numbers, symbols, and lines to identify components and show how they're connected electrically. The controller has a motor circuit or power circuit that provides power to the motor, and a control circuit that can open or close the power circuit. A power source, which is not shown on the diagram, is connected to the power circuit through the line leads labeled L1, L2, and L3. The line leads are connected to 3 main contacts, which are labeled with the letter M. The main contacts are normally open, which means that they're open when they're in the relaxed or de-energized state. The main contacts are connected to 3 overload devices, which are connected to 3 motor leads labeled T1, T2, and T3. The motor leads are connected to the motor. A step-down transformer is also connected to the power circuit. The transformer lowers or steps down the voltage used in the power circuit to a lower value that is used to operate the control circuit. The transformer is connected to a fuse. The fuse protects the motor controller from short circuits. If a short occurs in the control circuit, the fuse will blow, causing an open in the control circuit. The fuse is connected to stop and start buttons. The control circuit also has an operating or M coil and 3 overload contacts. The overload contacts, which are labeled OL, are normally closed. Pushing the start button energizes the control circuit, including the M coil. All of the contacts labeled M are operated by the M coil. When the M coil is energized, it closes the M contacts, and power can be provided to the motor. In this example, the start button is designed to be pushed in and released. After the start button has been released, maintaining contacts, labeled capital M, small a, remain closed to maintain current flow to the M coil. The maintaining contacts are auxiliary contacts operated by the M coil. If an overload occurs, the overload devices open the overload contacts. Opening the overload contacts opens the control circuit, which stops current flow to the M coil. When the M coil is de-energized, the M contacts open. As a result, the path for current to flow to the motor is interrupted and the motor stops. In order to stop the motor during normal operation, the stop button is pushed. Pushing the stop button opens the control circuit, which stops current flow to the M coil. Now, DC motor controllers are very similar to AC motor controllers. We can use a simplified diagram to see what we mean. Generally speaking, DC motor controllers differ from AC motor controllers in that DC motor controllers use direct current instead of three-phase alternating current. There are only 2 lines in the power circuit of a DC motor controller instead of the 3 lines in an AC motor controller. And DC motor controllers do not use a step-down transformer. The control circuit of a DC motor controller operates using the same level of voltage that powers the motor. Motors are rated to deliver a certain amount of power. If demand on the motor increases, current flow through the motor increases. If the current is allowed to exceed the rated capacity of the motor, it can cause serious damage to the motor's windings. To prevent such damage from occurring, overload devices are installed in most motor controllers. Overload devices protect motors from excessive current. Whenever an excessive current condition occurs, an overload device opens the circuit that supplies power to the controller's contactor or M coil. The de-energized contactor then opens the contacts in the motor controller, interrupting the current flow to the motor, and the motor stops. Overload devices can basically be divided into 2 types: thermal overload devices and magnetic overload devices. Both types of overload devices operate on current. Thermal overload devices operate on the heat generated from current, while magnetic devices operate on the magnetic field generated by current. Thermal overload devices use a heating element, often referred to as a heater. Current flowing to the motor first flows through a heater where it generates heat. The greater the current flow, the more heat is produced. When the level of current flow causes enough heat to be produced, the overload device is activated. We'll look at 2 common thermal overload devices: alloy thermal overload devices, which are commonly called solder pots, and bimetallic overload devices. This is a simplified illustration of part of a solder pot. We can see it has a heater, a ratchet wheel, a rod, and solder, which is an alloy that surrounds the rod. Current in the motor controller's power circuit going to the motor flows through the heater. When current flows through the heater, it generates heat. If the current exceeds the rated value of the overload device, enough heat is generated to melt the solder. Now let's look at the entire solder pot. From this angle, we can see the top of the ratchet wheel here. We can also see that the solder pot has a mechanical linkage, movable contacts, which are in the motor controller's control circuit, and 2 springs. The ratchet wheel, which is set on the rod, holds the mechanical linkage in place. The movable contacts are attached to the mechanical linkage, and the stationary contacts are positioned in the casing of the overload device. The linkage spring holds the mechanical linkage against the ratchet wheel, and the contact spring pushes against the movable contacts. While the solder is solid, it prevents the ratchet wheel and the rod from turning. As long as the ratchet wheel and the rod do not turn, the contacts remain closed and a complete circuit to the motor controller's main contactor, or M-coil, is maintained. The contact spring is positioned so that its force works on the mechanical linkage to attempt to turn the ratchet wheel. When the current level causes the heater to generate enough heat to melt the solder, the liquid solder cannot hold the rod, so the force of the contact spring causes the ratchet wheel to rotate. As the wheel turns, the linkage moves, opening the contacts of the overload device and interrupting the current flow in the control circuit to the M-coil. As a result, contacts in the motor controller are opened, which interrupts the current flow in the power circuit to the motor, and the motor stops. When the current in the power circuit stops flowing through the heater stops generating heat. When the heater stops generating heat, the solder then cools and becomes solid again. When a reset button is pushed, the contacts of the overload device close, which makes it possible to restart the motor by supplying current to the M-coil. Another typical thermal overload device is a bimetallic device, like the one illustrated here. This device consists of a heater, which is in the motor controller's power circuit, a bimetallic strip, which is a strip made up of two different metals that are bonded together, a spring-loaded mechanical linkage, a set of contacts, which is in the motor controller's control circuit, and a reset button. The two metals in the bimetallic strip expand at different rates when the strip is heated by the heater. Under normal circumstances, the bimetallic strip holds the mechanical linkage in place, keeping a set of contacts closed so that there is a complete path for current to flow to the motor controller's M-coil. When the current level in the power circuit exceeds the rated value of the overload device, enough heat is generated by the current flow through the heater to cause the bimetallic strip to bend so that it releases the mechanical linkage. The strip bends because the two metals in the strip expand at different rates. When the mechanical linkage is released, the force of the springs pulls the contacts open, which interrupts the current flow in the control circuit to the controller's M-coil. As a result, contacts in the motor controller open, which interrupts current flow in the power circuit to the motor, and the motor stops. When the current flow in the power circuit is interrupted, current does not flow through the heater, which stops producing heat, and the bimetallic strip cools. As the strip cools, it contracts and straightens. When the reset button is pushed, the mechanical linkage is moved against the force of the spring so that the linkage is snapped back into its original position. The bimetallic strip once again holds the linkage in place. The linkage holds the overload device's contacts in place, which makes it possible to restart the motor by supplying current to the M-coil. Now that we've looked at thermal overload devices, let's look at a typical magnetic overload device. You may also hear magnetic overload devices called magnetic overload relays. This simplified illustration of a magnetic overload device shows a coil around a metal core and a set of contacts. The contacts are held together by a spring. The overload device's coil is in the motor controller's power circuit, and the contacts are in the control circuit. When the power circuit is energized, current flows through the coil, creating an electromagnetic field. The strength of the electromagnetic field increases as the current level flowing through the coil increases. When the current level gets too high, the strength of the electromagnetic field increases enough to overcome the force of the spring and pulls the contacts apart, which interrupts current flow through the control circuit. As a result, contacts in the motor controller open, current flow to the motor through the power circuit is interrupted, and the motor stops. When the current flow through the power circuit and the coil stops, the electromagnetic field is also interrupted, and the force of the spring pulls the contact back to its original position. In this topic, we looked at the parts and functions of motor controllers and at typical overload devices used to protect motor controllers from overload conditions. Take some time now to try some practice questions that relate to this material. The steps we'll look at for a motor startup are intended as general guidelines that can be applied to starting most AC or DC motors. Keep in mind, though, that they're not intended as a substitute for your facility's procedures. And always keep safety in mind. Motors can pose a number of safety hazards. Loose clothing, for example, can get caught in rotating equipment. During pre-startup checks, the motor, the equipment that the motor is driving, and the rest of the system should be checked. We'll focus, though, on the steps that are concerned with the motor. One important pre-startup check is to check the motor's lubrication system. For proper operation, bearings must be kept lubricated. Lubrication reduces friction between the bearings' parts. Some motors use sealed bearings that do not have to be relubricated for the life of the motor. The bearings of some other motors are greased through grease fittings as part of a regular maintenance schedule. Some motors use constant level oilers, also known as bottle oilers, to lubricate their bearings. The design of the constant level oiler allows the operator to look at the level in the reservoir and add more oil when necessary. When a constant level oiler is used, oil flows into the bearings by gravity. Another important pre-startup check is checking the motor's cooling system. For example, this motor is cooled by a fan mounted on its shaft. The motor's ventilation openings are checked to make sure that they're clear of obstructions that could restrict cooling airflow. It's also a good idea to check the wires and conduit associated with the motor for signs of damage. Damaged conduit or loose or frayed wires may result in electrical problems. Some motors may have a grounding strap or ground wire that helps prevent electric shock hazards. It should be checked to make sure that there is a secure connection between the motor and ground. In addition, the motor should be inspected carefully for anything out of the ordinary, such as loose or missing components. The motor controller should be checked to make sure that it's energized and ready for the motor to be started. Depending on your facility's procedures, you may need to notify the control room operator before the motor is started. When all checks are complete, the motor can be started by pressing its start button. Once a motor has been started, it's important to make some operating checks to ensure that the motor operates properly. Operating checks are a vital part of keeping process operations running smoothly. By making these types of checks periodically, an operator may spot potential problems before they become serious. Typically, operators routinely check for proper lubrication, excessive or unusual noise, and excessive heat or vibration. Proper lubrication is an essential part of good motor operation. There are some motors that use sealed bearings that do not have to be relubricated for the life of the motor. Other motors rely on a lubrication system to supply the bearings with grease or oil. If the motor uses a lubrication system, it's important to know how much oil or grease a motor is using. If the motor seems to be using an excessive amount of lubricant, check for leaks. Motors get hot during operation, and they may overheat for several reasons. For example, an overload may result when an excessive load is placed on the motor. You can carefully feel the motor casing to determine if the motor is too hot. In general, if the casing is significantly hotter than it was during previous checks, there may be a problem. You may also be able to detect excessive vibration, which is another common motor problem, by carefully feeling the motor's casing. You should also look over the motor and the equipment it's driving for anything unusual, such as sparking or arcing, which could indicate a short or an open. In addition, listen for unusual sounds. A properly operating motor should make a smooth, steady sound. Excessive noise, knocking, or popping can be a sign of a problem. In addition to looking and listening for symptoms of motor problems, you can also use your sense of smell. Unusual odors may indicate a problem. For example, overheated insulation has a distinctive scent that can indicate a problem, such as an electric short. Now, when you're ready to shut down a motor, you first determine the impact that the shutdown will have on the system. Then prepare the system for the shutdown. For example, valves and switches in the process the motor serves may need to be properly positioned before shutdown. Finally, push the stop button for the motor. In this topic, we looked at typical steps for motor startup, and we looked at operating checks that can be made to ensure the proper operation of a typical motor. We also talked about what's involved in a motor shutdown. Take some time now to answer some practice questions that relate to this material. Physically, a motor controller may be located quite a distance away from the motor that it controls. Electrically, the motor controller is located between the facility's power supply and the motor. Pushing the start button energizes the control circuit, including the M coil. All of the contacts labeled M are operated by the M coil. We'll look at two common thermal overload devices: alloy thermal overload devices, which are commonly called solder pots, and bimetallic overload devices. Typically, operators routinely check for proper lubrication, excessive or unusual noise, and excessive heat or vibration.